In part 1 of this lecture, the fundamentals related to fatigue loading have been discussed. Now in this part, we will develop the design equation for fatigue loading, and an illustrative example will be presented to explain the application of the design equation. The design equations will be developed for the case when the part is subjected to static and alternating state cycles together. Then we will discuss the design for finite life, and then some guidelines for a better fatigue design will be presented. Fatigue test results of large number of experiments conducted with various combinations of mean stress sigma m and alternating stress sigma a for failure at a specified number of cycles, say 10⁻⁶ or 10⁻⁷, are plotted in figure 9. In the figure, the horizontal axis is that of mean stress sigma m and the vertical axis is that of the alternating stress sigma a. The curve through the failure data points is a parabola and it is known as Gerber's parabola. It passes through the endurance limit sigma En on the y-axis, where the mean stress is 0, and the ultimate strength sigma u on the x-axis, where sigma a is equal to 0, that is, loading is static. Then you can see there are two more lines. One is designated as Goodman line, another is Soderberg line, are shown on the figure. The fundamental equation of any line is x divided by a plus y divided by b is equal to 1. Hence, equation of the Goodman line joining the points 0 sigma En and sigma u 0 would be sigma m divided by sigma u plus sigma a divided by sigma En is equal to 1, and the equation of the Soderberg line extending from 0 sigma En to sigma y0 is sigma m divided by sigma y plus sigma a divided by sigma En is equal to 1. As discussed in part 1 of this lecture, the endurance strength sigma En is affected by the type of loading, size of the specimen or the machine part, the surface finish and stress concentration. Hence, the Soderberg relation is modified for design application, and on introduction of the factor of safety n, the relation becomes sigma m divided by sigma y plus kf multiplied by sigma a divided by RABC sigma En is equal to 1 by n. The equation is shown in figure 10. It is to note that alternating stress has been multiplied by the fatigue stress concentration factor Kf. Since this equation consists of the yield strength sigma y, hence it is applicable to ductile materials. For brittle materials, sigma y is to be replaced by sigma u, and the design relation is as under. Note that for brittle materials, both sigma m and sigma a have been multiplied by the theoretical stress concentration factor Kt. Similarly, for shear loads, the equation is tau m divided by tau y plus kf tau a divided by rbc tau en is equal to 1 by n. Here, tau En is equal to A sigma En, hence the factor A has been omitted. After developing the design equation, now we can consider an illustrative example. A uniform circular cross-section horizontal cantilever of 300 mm length is subjected to a transverse load at its free end, which varies from 100 Newton upwards to 200 Newton downwards, and also an axial load whose mean is 0 and alternating component is 300 Newton. The cantilever is to be made of C20 steel with ground surface. Determine the diameter of the cantilever for infinite life. For C20, the ultimate strength is given as 440 MPa. The yield strength is 250 MPa. The endurance strength is 190 MPa. A factor of safety of 2.5 is suggested. The maximum bending stress. Mean transverse load is half of 200 plus minus 100 because 100 Newton load is acting in opposite direction. This gives the mean transverse load as 50 Newton, and alternating component of this transverse load comes out to be half of 200 minus 100 is equal to 150 Newton. Mean component of the bending moment at section AA is load multiplied by the distance 300 mm. So mean component is 50 into 300, that is 50 into 10 raised to 3 Newton mm. The alternating component of the bending moment at the section AA is MA is equal to 150 into 300, that is equal to 45 into 10 raised to power 3 Newton mm. Now the mean and alternating stresses due to bending loads can be calculated by dividing the bending moments by section modulus of the bar. Thus we have sigma m is equal to mm divided by z is equal to 15 into 10 raised to power 3 divided by 5 by 32 d cube, which is the section modulus for circular cross section bar, and sigma a is equal to me divided by z. Now we calculate the direct stress. The mean stress in axial direction is 0, and in axial direction only alternating component is acting. So sigma a axial is equal to Fa divided by area of cross section pi by 4d square of the bar. For C20, which is a ductile material, Soderberg relation applies. Hence for combined bending and axial stresses, the equation gives sigma m divided by sigma y plus kf divided by rbc sigma en, sigma a divided by the type of load factor A for bending, and sigma a divided by A axial is equal to 1 by factor of safety. Remember that the type of loading factor A for bending and axial are different. Where Kf is equal to 1, there is no stress razor. R is equal to 1 assumed, B is equal to 1 for trial, and C is equal to 0.9 for ground surface from figure 7. A is equal to 1 for bending and 0.9 for axial load assumed. Substitution gives for factor of safety n is equal to 2.5 the following relation. The solution of the relation by trial and error gives the required diameter as 20.3 mm. Since the size factor B is approximately 0.95 for D approximately 20 mm, retrial with B is equal to 0.95 gives the bar diameter approximately 21 mm. In the previous sections, we considered the design for 10⁻⁷ or greater number of cycles. In the case of ductile metals, a design for greater than 10⁻⁷ cycles gives an infinite life. Such design for infinite number of cycles of loading or infinite life is based on the endurance strength sigma En. However, some machine components are to be designed for a finite life, that is less than 10⁷ cycles. In such cases, the design point lies left to the vertical line AA in figure 13 and the allowable stress sigma is greater than sigma En. Basquin proposed an equation to represent the part of the sigma n curve in the region n less than 10⁶. The equation is sigma is equal to a n power b, where sigma is the reversing stress which will give a fatigue life of less than 10⁶ cycles of loading. In the equation a and b are two constants. The log of equation 1 gives log sigma is equal to log a plus b log n. Basquin considered sigma is equal to 0.9 sigma u for 10⁻³ cycles and sigma en for 10⁻⁶ cycles. For these values, equation 2 gives a is equal to sigma en divided by 10⁻⁶b and b is equal to 1/3 of log sigma en minus log 0.9 sigma u. Knowing the constants a and b, the stress sigma for life less than 10⁻⁶ cycles can be found from equation 1. Here are certain guidelines which can lead us to better design against fatigue. By certain modifications in the design configuration and proper selection of material, manufacturing methods and heat treatment, the fatigue resistance of a machine can be improved. The methods are: avoid stress reserves by proper design of the part and make the configuration of the part as simple as possible. If stress reserves cannot be completely avoided, the effect can be reduced by using fillets or making gradual change in the section. Refer figure 12a. Modify to reduce the effect by providing proper deconcentrators to decrease the curvature of the force flow lines as shown in figure 12p. Processes such as short pinning that induce compressive stress on the surface to decrease the intensity of tensile stress. Materials with high fatigue strength should be selected. Make careful selection of manufacturing processes. For example, forged components have better fatigue resistance. Polished and ground surface of a part improves the fatigue strength. Residual tensile stresses on the part should be relieved by proper heat treatment. Surface hardening using carburizing, nitriding or induction hardening enhances fatigue resistance. Induction of compressive stresses on the surface by short pinning is frequently used to improve fatigue resistance of springs. Parts should be protected from corrosive atmosphere. Welding reduces fatigue limit. The problem can be minimized by careful design and manufacturing control. This lecture defined the fatigue limit and fatigue or endurance strength and discussed the various factors that affect the endurance strength of a material. Design of the components subjected to fatigue loading has been discussed for the loading cycle, which can be reduced to a combination of the mean and alternating stresses. An illustrative example has been included to explain the use of the design concept. Design of parts for finite life when subjected to completely reversed cycle loading has been presented. In the end, the lecture discusses the various methods to improve the fatigue resistance of a machine part. More discussion on fatigue design will be made when designing various components. More details can be seen in the reference given here. I hope you have liked the video. Please feel free to send your questions at my email address given on the first page. Please wait for more videos. Thanks.